All right, perfect. So we're ready to move on to the next speaker, which is Markus Dierigl, who's going to tell us about useful Bordism defects. I hope it's very useful. Thank you.
Thank you very much. So first, big thanks to the organizers for setting up this beautiful conference. So indeed, today I will talk about work in progress together with Noah Brager, a grad student from UPenn, Aaron Debray, mathematician who is in Purdue University, Jonathan Heckman at UPenn, and Miguel in Madrid. And it's also related to earlier work that was published last year. So I guess everybody in this room would agree that string theory is a consistent theory of quantum gravity that produces a lot of interesting things, right? So for example, you have p-branes that are nice backgrounds that engineer gauge theory sectors. You can build CFTs in high dimensions that are interacting using, for example, non-Higgsable clusters. You have these exotic supersymmetric theories with n equals 3 supersymmetry that are produced by S-folds. And you can do topological twisting to produce some interesting sectors that you can study in detail and so on and so forth. But you might ask the question, well, are we missing something? Are we missing some sector of string theory that would produce something interesting that we don't know about yet? Right? And if so, how do we find out? So what I'm going to do in this talk is actually I apply Swampland criteria, so universal criteria that should hold in any quantum gravity theory, and I'll apply it to string theory. So what kind of Swampland criterion am I referring to? So I'll use the no global symmetries conjecture, and in particular I'll use the formulation in terms of this cobordism conjecture by Kamran and Jake McNamara. Okay? So what does that mean? Well, think about a compact space-time manifold, right? It's part of a bigger space-time potentially that you cannot deform away, so you cannot deform it to a point. If such a background exists, then you can associate it to a conserved charge and correspondingly a global symmetry, right? So what this cobordism conjecture tells you is that every compact space that is okay in the notion of quantum gravity theory you're working with should be deformable to nothing, right? Otherwise, there is some topological obstruction for that that can be interpreted as a conserved charge and a global symmetry. So what is the input data that you put in there? Well, you define a low energy effective description, right? That comes with some information that you need on your space-time manifold, on your geometry, for example, orientability or spin structure. And then you have a bunch of gauge fields that you want to include. So also that goes into the definition of the data. And then you can calculate an object in mathematics, which is the Bordism group. It's the group of different deformation classes, right? So if you only have the trivial deformation class, that means that you can deform everything away and there is no conserved global charge, no global symmetry, you're happy. But if it happens so that this is a non-trivial group, you have to do something, right? So let's say you have this circle and you cannot deform it to a point, then you would associate a global charge to this object. And in order to get rid of this global charge, to break the associated global symmetry, you have to introduce a new object. And for example, that is denoted by this red dot, and if you include it at the tip, then suddenly this deformation is possible, the global symmetry is broken, everything is fine. Now these objects, they appear as naturally singular in the IR description that you chose in which to define the gravitational and gauge field data, right? But they become dynamical objects in the UV complete theory. So now the strategy today will be, well, first set up this low energy effective description and the necessary structures that we input for our calculation. Then determine the global symmetries in this sector, right, via calculating the Bordisms, and then make sure that string theory knows about the symmetry breaking objects. So we put a test to string theory, or rather maybe our knowledge of string theory. Do we know everything we need to know in order to get rid of these global symmetries? Now the setup I will choose is maximal supergravity in 10 and in 8 dimensions. And the input data is the space-time geometry plus the duality bundle. Okay? And the duality bundle, yes? That's right. So in principle, there is the option that instead of breaking the associated global symmetries, you can gauge it. So in terms of the cobordism conjecture, that would tell you that you include rules that basically localize your theory on the charge 0 sector. That would be the gauging. Often if you do that dynamically, because you want to implement it in a way that the theory does it itself, then a dual symmetry will emerge. But indeed, today I will only talk about the symmetry breaking of the cobordism conjecture. So yes, the input data, as I said, is space-time geometry plus duality bundles, and that's also where the title comes from, because in 8 dimensions, the dualities are called U-dualities, right? So that's the useful Bordism defect that I will come to. So first step, 10D supergravity. So we want to work with type 2B supergravity that has a 2,0 supersymmetry and has an interesting duality group, which is SL2Z. And then you can also include the orientation reversal of the string worldsheet omega. However, since the duality acts differently on the bosonic than the fermionic particles, you actually have to do what is known as a spin lift, or if you include also this orientation reversal, a pin plus lift of this duality group. I will not go into the details here. Now, this just means that in the end, the objects that you want to compute are these following Bordism groups, is d-dimensional Bordism manifolds that have a spin structure that mix with the duality structure, either without the orientation reversal or with the orientation reversal. These you can compute. It's hard, but there is algebraic topological techniques like the Adam spectral sequence or the Atiyah-Hirzebruch spectral sequence that you can run, and you can determine those groups, and they turn out to be highly non-trivial. So there's a lot of global symmetries that you should worry about, right? And if we focus first on this piece here, that's the spin MP, that's the one without the orientation reversal for the worldsheet, we can now ask, well, do we know about string theory objects that act as this symmetry breaking pieces that allow the deformation to nothing? And indeed we do. So you can basically kill all of those classes, and what you find is PQ7 branes, you find non-Higgsable clusters, you find S-folds and generalizations thereof, you find topological twists. So essentially you find all the interesting ingredients I had on my first slide that are now necessary in order to make sure that string theory doesn't have global symmetries. But we know about all of this. It points in interesting directions, and string theory does the job here, right? So now if we go to include this orientation reversal, so we go to spin GL plus Bordisms, then there is one thing we don't know. Or at least it has been hinted at in a paper by Jacques Fried and Greg Moore here a while ago. And this new object is a U-7 brane that was not really formulated in string theory before. And the reason is it has weird properties. Namely, it breaks supersymmetry completely, so it will not act like a PQ7 brane that preserve half of the supersymmetry and our BPS states, so it's a little bit exotic in that regard. It's even more exotic because D3 branes can end on it, as we have shown by some Lasso type of argument, and it can be used to construct symmetry operators for interesting theories, as is done in this generalized symmetry approach, right? But including this single new object, the R7 brane, and a bunch of new backgrounds that come from orientation reversals, such as O-planes that we know about, the picture looks like this. All the symmetries are gone. Well, not really all the symmetries. Curiously, these infinite factors here, so those would correspond to a continuous U1 symmetry, right? They are very hard to kill. So they are associated to, so if you look at this, they're associated to something like the first Pontryagin number of the space-time manifold, and in dimension 8, it's the first Pontryagin number squared or the second Pontryagin number. Those are very hard to kill. We don't know a background. Is it because they are related to a continuous symmetry? I'm not sure. It's an interesting problem for you and for me, of course, as well. But all the other ones, the discrete ones, are gone by basically all the stuff that we know plus a single new object. So that string theory is doing actually quite good here. Very impressive, impressively so. Now let's go to the next step, which is 8-dimensional supergravity. Right? Again, maximal supersymmetry, so n equals 2 in 8 dimensions. And now we have this U-duality group, which in 8 dimensions reads SL2Z times SL3Z. Okay? Now the problem is there should be a non-trivial lift to the action on fermions in the theory, but we don't know what it is. So let's stick for now on this bosonic duality group, and the associated Bordism group now is that of d-dimensional spin manifolds that have this duality bundle in this U-duality group here. While this SL2 factor is nice and easy because it has a decomposition into two factors that we understand well, that's called an amalgam decomposition. So it essentially splits into a Z3 and a Z4 part, which are well understood, and it's not so hard to work out. The SL3 is a completely different beast, right? It doesn't have an amalgam decomposition. It splits into other smaller non-abelian discrete groups, and it's very hard to run the spectral sequences. But we did so, and indeed we find again a lot of different global symmetries that appear for U-duality. But now you might, well, let's first go to a string theory description where how to see these groups arise. Right, so we're talking maximal supersymmetric supergravity in 8 dimensions that you can achieve by just taking 11-dimensional M theory and put it on a 3 torus. And that's what reproduces the SL3 factor as basically the large diffeomorphism that act on the 3 torus. Right, so there the SL3 is nice and geometric, whereas in type 2b, you take the type 2b in 10 dimension, you compactify on a torus, and you'll find the SL2 factor as the large diffeomorphism of the compactification torus. But you can do a little bit better because in type 2b you also have a non-perturbative description in terms of F theory. So actually there is a second torus, that's the F theory torus, which also produces another SL2Z factor, which sits inside the bigger one, right? So in type 2b you basically can achieve to geometrically describe this subgroup of the full U-duality group, and in M theory this part. Note, however, that there is no way that you can describe the full thing geometrically, which will be important later. Okay? Now you can ask, but wait, this is somehow weird what you're doing, right? You just told us in 10 dimensions there is no global symmetries. Now you do it in 8, which comes from a compactification. There shouldn't be anything new, right? Well, that's not true because the U-duality group now contains more transformations, different ones. It's not only the SL2Z, the strong weak coupling duality of type 2b, but there's also T-duality, like really stringy symmetries that appear now, right? So, and these might produce new backgrounds. So in the rest of the talk, what I want to answer is, well, what happens to the 10D defects now in the perspective of an 8D supergravity person? Do we find new stuff that we haven't found, new corners of string theory that we haven't found before? Do they all have a string interpretation, or do we need to include also new string theory object? And how does it behave on the duality? So let's go to the easiest object in real codimension 2. In 10 dimensions, we found the PQ7 branes, which just tells you that you have a circle, and around the F theory fiber undergoes monodromy, and we know we can fill it in, where at the tip of this cone will sit a PQ7 brane stack, right? And these are non-trivial. They have to be included in the 10D description, and the reason is the first Bordism group is associated often to the abelianization of the gauge sector. And the abelianization of SL2 is non-trivial. However, this SL2, this embeds into the SL3, and the abelianization of SL3 is trivial. So actually, this codimension 2 objects, they're completely gone once we go to 8D supergravity, because now we can close off this circle by putting a torus where we have a non-trivial SL3 transition function. So that's the new ingredient, right, that we didn't have in 10 dimension. But with this new freedom of having this more transformation, we can trivialize this background even without the introduction of a singular object. However, the PQ7 branes, they're not gone. In codimension 4, now they appear again. So there we have a generator that is a 3-dimensional length space around which this F theory fiber undergoes some monodromy. And indeed, that still survives down to the 8-dimensional supergravity description. And we find precisely the non-Higgsable clusters of 10 dimension now compactified on a 2 torus. Right? So that's precisely the compactification of the 10D defect. So sometimes important pieces of that really survives, and you rediscover what you found in 10 dimension. This also has a nice M-theory interpretation, because in M-theory, this torus is also part of space-time. And it's just M-theory or even type 2a, because one of the circles of the 3 torus is invariant, compactified on a singular elliptic Calabi-Yau threefold. Okay? Now, are there new objects? Yes, there are also new objects because now we have the action on space-time itself, right? So we have an action that really is not in the F-theory fiber, but is in this T2 that is part of the type 2b space-time, and produces new defects that look like local singular K3 manifolds that have this type of fiber structure. So the fiber degenerates to this torus-like orbifold and has 3 A2 singularities sitting at those orbifold points. So what we find is a new type, a new corner of string theory that we need to include, which is the n equals 2,0 SCFTs. Those didn't appear in the 10D description because we only found the 1,0 SCFTs. Now we find the 2,0s which come from geometry. These are non-geometric in M theory. They're geometric only in the type 2b framework. The other way around, there's also non-geometric stuff in type 2b that is geometric in the M theory, where you have a non-trivial action on the 3 torus that produces local singular Calabi-Yau threefolds of this type that are some notion of this 5D SCFTs, Seiberg theories, like E0. And this particular one is a twist of 3 of them into each other. So again, a new sector arises. We find new SCFTs, new interesting corners of string theory that weren't there in the 10D description. And finally, we had now, in one duality frame, it was non-geometrical, in the other one it was, but there's also backgrounds that are non-geometric in either one, right? So there's new non-geometric backgrounds, sometimes also known as these T-fold geometries, because you have transition function that act with T-duality. Which ones are necessary? So the classification is not fully done yet, but there is like hints that these are related to some sort of embedding of other defects into defects and so on. So there's a lot to be going on in these backgrounds. Now, do we need something really new in string theory? We've certainly found new corners, again, that we needed to include, but at the moment, it seems that we don't really need a fundamental new object in string theory to kill all the global symmetries associated to U-duality in 8 dimension, which is astonishing. So again, string theory our knowledge of string theory does a great job. It kills everything we needed to kill, right? But we find these interesting backgrounds of 2,0 SCFTs in 6D, this 5D non-geometry T-folds, and also, astonishingly, most of the backgrounds have a supersymmetric realization. A priori, there is no reason. We just put in topological information. There is no supersymmetry that we put in by hand, but all the defects that we constructed so far allow a description in a supersymmetric fashion, which might point at something. I'm not entirely sure. So lastly, let me just state one thing where you have to be careful is like if you want to really relate what the singular object in the string theory interpretation is, then duality is not always as helpful as you might expect, right? So we have sometimes this M theory description or the type 2b description, but usually they sit at different points in moduli space. So they're not naturally the same, right? So they're kind of the same, but often they're somewhere else, and you can sort of visualize it by this F-theory fiber, right? The F-theory fiber sits at 0 volume by default, whereas in the M-theory, it's part of space-time, it sits at a finite volume, right? So whereas a pinching of torus might produce a E6 gauge algebra on the F-theory or type 2b side, it looks more like 3SU3 algebras in the M-theory framework where this stays at a finite size. And it becomes even less clear in non-geometric backgrounds. So that's the easiest codimension 2 defect from the type 2b side in 8 dimensions. So that was this geometry where we had this orbifolded torus that you can resolve. That's the resolved A2 singularities that I showed you before. And you know what the SCFT sector is associated to that. And if you want to recreate it in M theory, you would say like, well, you have to put in a stacks of a couple of M5 branes because those correspond to this SCFT sectors. And while it is consistent with the bounding data that we know, it's far from clear and far from obvious that those backgrounds are related one-to-one. Okay? So there's just a little bit of a caveat there. So with that, let me summarize. So string theory does exceptionally well satisfying the cobordism conjecture. It really gives you all the objects that you need in order to break the global symmetries that would be there. And these symmetry breaking defects always point at an interesting corner, be it SCFTs or or topological twists and all the things I showed you before. Right? So now what else is there to do? Well, we don't know the spin lift of the U-duality group, so what happens if we do so? So that was where all the meat came from spin MP to spin GL, right? That was all the subtlety here. We can go down in dimension. The U-duality groups become bigger and bigger, and we can ask whether there are new objects to be found there. You can add additional structures. So I only had duality plus space-time. You can also add new fields like the Ramond-Ramond or a K-theory version of it. Calculations, of course, become more complicated, but would be very interesting. And then once you have the defect, it would be very interesting to study their properties directly and their effect on the duality. And that's all I wanted to say. Thank you very much.